Subscribers, so today what we're going to be looking at is section 3.4, which deals with elements and compounds. Now before we get into the details of these notes, there's a few objectives that I want you to be able to accomplish by the end of this lesson. So objective number 1 is to distinguish between elements and compounds. Objective number 2, describe the organization of elements on the periodic table. And objective number 3, explain how all compounds obey the laws of definite and multiple proportions. So let's get underway with elements and just have a basic definition here of what elements are. So elements are defined as a pure substance that cannot be separated into simpler substance by physical or chemical means. Now, currently, there's 91 elements that occur naturally on Earth. Now, other elements have been produced synthetically or man-made, and we'll see here in a few moments that there's actually 118 elements that are currently discovered. But again, elements 92 on are those man-made elements. Now, each element on the periodic table of elements has a unique name that is universally accepted by scientists. Now, the IUPAC, or the International Union of Pure and Applied Chemistry, is actually an organization that sets those names of those elements that we have on the periodic table. Now, each of these elements on the periodic table can be represented by a 1 or 2 letter symbol. Now, the first letter of the elemental symbol is always capitalized. However, always the second letter of that elemental symbol is lowercase. Now, another thing unique about the periodic table of elements is that naturally occurring elements are not equally abundant. So, for example of this, about 75% of the mass of the entire universe is from one element, and that is hydrogen. And here on Earth, the mass of Earth's crust is composed of about 75% of a mixture of oxygen and silicon. And there's only about 20 grams that's estimated of francium that exists on Earth's crust. So the whole point of this is that even though we show these elements, they're not equally present across the universe. Okay, so now that we've introduced what elements are, let's show you how they're organized. So how we organize the elements is into the periodic table. Now, the periodic table is going to organize the elements into a grid of horizontal rows called periods and vertical columns called groups. Now, we also sometimes call these groups in the periodic table our families. And we'll get more into detail about the specifics here of the periodic table later on in a different chapter. But we do have some unique characteristics of the periodic table. The first thing is that elements in the same group have similar chemical and physical properties. And then the other thing that's really unique is that we have a quote-unquote periodic pattern that occurs as you move from period to period, or left to right in a period. Now, the modern periodic table was developed by a Russian scientist named Dmitry Mendeleev. And we'll learn more about Dmitry Mendeleev and what he did to chemistry, but in general here, what he did was that he organized all of the elements that were known at the time into rows and columns based on the following two things. Number 1 was similar chemical properties. And then the second thing was on their masses. Now, Mendeleev wasn't the first person to organize the elements in a way or even in a table, but what made him prolific here was that he organized the periodic table so that he left spaces to accommodate for elements that had not been found or discovered at that time. And what's so amazing about this periodic table that was produced by Dmitri Mendeleev is that he was also able to predict the properties of these elements that were not discovered. The one he left spaces for, he's actually able to predict their properties down to some very specific details. So what the periodic table does is it gives us that power of prediction, and that's what Mendeleev set up, and that's what it allows us to follow. Now, they did make one minor correction to his periodic table, which we'll talk about later on, but a very significant point in science to have this tool to not only organize the elements, but to make it useful and to make it into that power of prediction. Now, what I have for you on the next page of notes is the actual periodic table. So I want to just highlight a few things. Number one, there are 118 elements, and element number 118 comes out to this portion here. So they've actually discovered all 118 elements. Number two, what we have here, just some basic setup, is our up and down columns are called our groups. So I'm going to turn this sideways and I'm going to draw an arrow. And again, these up and down columns are called the groups. And then your left to right sides, if we move from left to right in one individual row, these are the periods. And I'm going to draw an arrow once more. And these would be referred to as our periods. Now, what you may also encounter, and I'll often talk about this too, groups can be called families. And we went over that on the other page of notes. Now, what I want to highlight is a couple of things. And we go back over this more and more as we get in depth into the periodic table. But number one here is this whole number. Now I'm going to highlight beryllium as our example, but this whole number is what we call the atomic number. And I'm going to use the hashtag symbol for number. But the atomic number, I'm going to put in parentheses, is a whole number. Okay? Then what you have below there is either the 1 or 2 letter combination. So right here, and I'm going to use a different pen, right here for beryllium has the symbol Be. And so again, each and every element in the periodic table has a unique elemental symbol. And I want to emphasize this once again. It is a 1 or 2 letter combo. Now, we talked about this on the first page of notes, that the first letter is always capitalized. So I want you to take a look here on the periodic table. Notice every first letter is capitalized. The second letter, if it has one, it doesn't have to have one, but if it has that second letter, that letter is lowercase. Now, down below that is the elemental name. And I allow you to use a periodic table, so I expect these to be spelled correctly. Again, that is listed on this periodic table as the elemental name. And then our final item that I want to talk about here is normally a decimal number. So I'll circle this here For beryllium, it's 9.01 and some additional numbers here. But this number right here is the average atomic mass. And I'm going to put in parentheses because we've dealt with two numbers already, that the average atomic mass is normally a decimal. And we'll discuss why this is in a later chapter. But for right now, I want you to notice that the atomic number is a whole number. The element symbol is either a 1 or 2 letter combination. The element name is written on the periodic table that's provided. And then this decimal number, or the number that is usually the decimal, is that average atomic mass. Again, we'll have chapters where we emphasize the periodic table and we utilize this more and more. But this gives you a quick snapshot of the really important qualities or the really important information that is contained for each element of the periodic table of elements. So now that we have an idea what an element is, we can begin to think more realistically and a little bit more complex into what we can do with these elements. And what we can do is we can produce compounds. And so we start out here with what the definition of the compounds are. And compounds are simply defined as a combination of two or more different elements that are combined chemically. Now, compounds can be classified or are classified as pure substances. And like I said before, this is more realistic here because most of the matter in the universe is going to exist as compounds. And so there's numerous examples, but some of these examples include items like water, table salt, table sugar, and substances like aspirin. Now, just to give you an idea, there's approximately 10 million known compounds. And new compounds are discovered at approximately a rate of about 100,000 per year. Now, as technology increases and we get better and better products out there, we are able to increase the amount of compounds that we can discover each year. Now, I want to talk about the formulas of chemical compounds briefly. So for the formulas of chemical compounds, it's going to use element symbols from the periodic table to write the formulas of chemical compounds. And the best way to see this is through some examples. So number one, a good example is sodium chloride, or typical table salt. That is composed of 1 part sodium and 1 part chlorine. Another good example is pure water, or H2O. In this formula, H2O is composed of 2 parts of hydrogen and 1 part oxygen. Alright, so in section 3 and in section 4, we talked about a couple different forms of matters. And the two main forms of matters was mixtures and pure substances. And we've talked about many of each. And so I want us to be able to distinguish or determine when we have a mixture versus when we have a pure substance. So what I've provided you is this flow chart that can be used for this. So remember, matter is anything that takes up space and has mass. It can be classified in these two general categories. Mixtures we talked about in section 3. Pure substances we talked about just now with our elements and our compounds. Now, we can further break our mixtures if we determine it as a mixture and can be separated into that heterogeneous and homogeneous mixtures. So remember, heterogeneous, you can essentially see those clumps, something like salad. Homogeneous is consistent throughout, so something like soda pop. Now, pure substances have to do with elements and compounds. So elements, remember, if it's that element and only one of those elements by itself, it can be classified as an element. But if it's an element where we combine two or more elements chemically, we have a compound. So let's go into our details about our properties of compounds. So our compounds, like I said, they are composed of at least two elements that are chemically combined. And these properties, we need to note this, these properties are going to differ from those individual elements. And we also have to keep in mind that chemical compounds are produced from a chemical reaction. Now, with compounds, they can be broken down into simpler substance by chemical means. Now, this separation of those individual elements is going to require energy, typically in the form of heat or electricity. Now, it's also important to note that naturally occurring substances are usually more stable than the individual component elements. A good example of that is salt, sodium chloride, or water, H2O. Both of those substances are much more stable as a compound. And so let's take an example look, or a look into one of those examples I just listed with sodium chloride. Now, sodium chloride is going to have different properties than individual elemental sodium and individual elemental chlorine. So, for example here, sodium is a very highly reactive element that if you place it in water, it's going to fizz and burn in that water. And chlorine is a poisonous pale green gas. However, when you chemically combine sodium and chlorine, you produce sodium chloride, which is a white, unreactive solid that flavors many foods. Now, the difference in these properties between individual elements and their compounds here is a result from a chemical reaction between those elements involved in the compound. Alright, so we've looked at a couple compounds, and like I've said before, they have this defined exact ratio. And because they have this defined exact ratio, we can have this law of definite proportions. So the law of definite proportions is defined as a scientific law, that states a compound is always composed of the same elements in the same proportion by mass, no matter how large or how small that sample of the compound is. Now, these relative amounts of a compound are expressed as percent by mass. So with that being said here, that brings us to another important point, and that point is percent by mass. So the percent by mass can be defined as a ratio of the mass of each element to the total mass of the compound expressed as a percentage. Now, again, that definition is great, but this is a mathematical concept. So with that mathematical concept, typically we have a formula, and we do here. And so the formula for percent by mass, I'm going to use the symbol percent by mass. That is equal to our mass of the element that we are looking at divided by the total mass of the compound we have present. And then we multiply that by 100 to get it into percent. So I always like to have some steps to be able to solve our mathematical operations. The first two steps are, number one, determine the mass of the individual element, and number two, determine the mass of the entire compound. Once you've determined those values, you need to plug them back into the percent by mass formula. Once you have them back into that formula, you simply solve mathematically. Okay, so let's put this formula to the test in a couple example problems. Okay, so example problem number 1 says we have a 78-gram sample of an unknown compound. This compound contains 12.4 grams of hydrogen. We want to know the percent by mass of hydrogen in the compound. So again, I always like to start out by writing my formula. So this specifically is percent by mass of the specific element hydrogen. So what we're going to do here is we are going to put the mass of hydrogen on top, and then on bottom there we are going to put the total mass of the compound. So we can't forget about this, we're going to multiply this by 100. All right, so we move down here. We don't know the percent by mass of hydrogen yet, but we do know the mass of hydrogen. If we read very carefully here, it says we have 12.4 grams of our hydrogen, okay? So I'm going to put 12.4 grams of H. Remember, H is that symbol for hydrogen. And then on bottom, I'm going to put the total mass of the compound, which it's a 78.0 gram sample. So I'm going to have 78.0 grams. And then again, very important that we don't forget about that multiply by 100 to get us into percent by mass. All right, so in my calculator, what I'm going to do first is I'm going to take 12.4 divided by 78.0, and I'm going to press enter. Now, before I do anything else, I'm going to multiply by 100. And I'm going to round to 3 significant digits, which in this case would give me 1 decimal. So our percent by mass of hydrogen is 15.9%. Again, we put hydrogen in here because that is the specific element we are wanting to find the percent by mass. So what this means is that whatever compound we're dealing with, which we're not given what compound we have, but no matter what, this compound will always have 15.9% by mass of hydrogen. It's a very effective way we can distinguish one compound from another. All right, let's try another example. This time it says if 1 gram of hydrogen reacts completely with 19 grams of fluorine, we want to know the percent by mass of hydrogen in the compound that is formed. So once again, we are going to identify the percent by mass of hydrogen, but we're going to have to do it a little bit differently. Now, to orientate us to this, I'm going to put the mass of hydrogen on top and the mass of the compound will be below. We can't forget to multiply this by 100 to get it to percent. So again, we don't know the percent by mass of hydrogen because that's what we're trying to solve. So we go through this, the percent by mass of hydrogen is equal to this. Number one, we need the mass of hydrogen. Well, it says here we have 1 gram of hydrogen. So we have 1 gram of H. Then we divide it by the total mass of the compound. Well, you have to be careful here because in the problem it doesn't say the total mass. But it does give us the two things that reacted? Well, remember, products and reactants have to have equal masses. That's the law of mass of conservation of matter. Okay, so what that means is we have to have 1 gram from hydrogen plus the 19.0 grams of fluorine. Now again, we need to multiply this by 100, but because we have a mathematical operation on bottom there, we need to put that business in parentheses. So when we go to find percent by mass of hydrogen, what we're going to do is we're going to take 1.0. We're going to divide it by 1.0 in parentheses. Notice how I did that. Plus 19.0. And we're going to close that parentheses. Now, remember, we need to multiply this by 100. And so we would get an answer of 5.0. So the percent by mass of hydrogen for this specific compound would be 5.0%. Now, what that means is that in this compound, no matter what sample we have or how big or how small, 5% of it is going to contain hydrogen. All right, so now with compounds, now because we've talked about compounds a little bit more, we can talk about one more law. And that law is the law of multiple proportions. So the law of multiple proportions is going to state that when different compounds are formed by a combination of the same elements, different masses of one element combine with the same relative mass of elements in whole number ratios. Okay, so that's a lot of jargon there. That's a lot of words to explain this. The best is to go through some examples. So let's compare hydrogen peroxide, which has the formula H2O2, and water, again, have the formula of H2O. So the first thing to identify is that both of these compounds here are going to contain hydrogen and oxygen. Now, if we look into water, we need to identify that water has 2 parts hydrogen to 1 part oxygen. Now, hydrogen peroxide has 2 parts hydrogen to 2 parts oxygen. And so the important part here out of this whole example is that hydrogen peroxide is going to contain twice as much oxygen compared to that of water. So overall here, the mass of oxygen in hydrogen peroxide to the mass of oxygen in water has a ratio of 2 to 1. All right, so all of our jargon here that we wrote up to define the law of multiple proportions comes down to this ratio. So if we have 2 compounds with the same elements, we can compare and contrast what is the ratio of one amount of element to that same element in another compound. So again, bottom line up front here is this is just a way to find out a ratio to compare similar elements in different compounds. Let me show you one more examples with a little bit more mathematical concepts. Okay, so we have copper 1 chloride and copper 2 chloride. So I want to write out the formulas here for copper 1 and copper 2. So copper 1 has the formula of CuCl, and copper 2 has the formula of CuCl2. Okay, so copper 1 chloride is going to have half as many chloride ions or Cl's as copper 2. A better way of putting that here is that copper 2 chloride would have twice the amount of Cl1 we call them ions, but amount of Cl compared to copper 1. So this is why when we have the mass ratio as shown in these charts in this calculation here, this is why the mass ratio of Cl in copper 2 chloride to that in copper 1 chloride has a ratio of 2 to 1. And again, this should be mass ratio of 2 to 1 of copper in copper 1 chloride compared to that of copper 2 chloride. Again, don't get caught up too much in the math. Just know all we're doing is we're comparing how much of each element is in a compound with the same type of elements. Big thing there is, hey, we can have the same elements in different compounds. This mass ratio of those elements is going to be slightly different. All right, so that's everything that is covered not only in section 4 but in chapter 3. As always, I hope you have enjoyed this particular episode, and if you haven't done so already, make sure you subscribe.